Okay. So we wrote last time the is out of balance, right? To determine whether something is out of balance. And I think that, what did I say, in the, you could just print out to the console or whatever the solution here. You didn't have to add anything to the interface, right? So what we're trying to do is we're trying to determine, once it's out of balance, how is it out of balance? Is it out of balance? Is it heavy on the left or is it heavy on the right? So what are some approaches we can take to accomplish this? Go ahead. It means if we're out of balance, that means one side is greater than one, bigger than the other side, right? Herein is out of balance, we have the left depth and the right depth. And we're just, so we're getting the difference here, which is the absolute value of the two subtracted from each other. And then we're just returning whether that difference is greater than 1. If the difference is greater than 1, that means we are out of balance, correct? So if we are out of balance, we would then further be interested in knowing how we're out of balance. So if I came in here and I asked, are we out of balance? Instead of just returning true or false here, if I ask the question, if the difference is greater than 1, that means we are out of balance, right? So now the question is how are we out of balance? Okay, so if left is greater than, or left depth is greater than right depth, system.out.println, I'm going to put a bunch of asterisks before it. Out of balance left, else out of balance right, regardless, we're going to still return true. And if we're still kicking out here, we'll return false. So if we are out of balance, if the difference is greater than 1, we're going to print out if the left side, if the left depth is greater than the right depth, then we're out of balance left. Otherwise, we're out of balance right. Regardless of which of those two we print out, we'll return true because we are out of balance. If we didn't get inside this if statement, that means we're not out of balance. We'll just return false. Yeah.
Isn't there technically a mathematical error with the difference being greater than 1 then? Because if you're doing left depth minus right depth, and if right depth is bigger than left depth, we're doing negatives. Oh.
Yeah, it takes the absolute. Yeah, we take the absolute value of it. But yeah, you're right. Otherwise, yeah, that's why we do the absolute value of it. Remind me again. Is this a class method or instance method, and how do you know? Class method. How do you know?
Called by the name of the class.
We're calling it using the name of the class in which it was probably defined. So math. How do you know math is a class name? What lends you to believe it's likely a class name? A couple of evidences.
It's got a method name that follows it, right?
Yeah, but you can have instances that have method names that follow it. You know, we have one of those right out here inside of main activity. Isn't this a instance name? And here's a method that follows it. Because this guy would actually be an instance method. Because we're calling it using an instance of the class in which it was defined, as opposed to, he pointed out that this guy over here is a class method because we're calling it using the class name. So then I followed it up and said, well, how do we know, or how can we strongly suspect that this guy is a class name?
It's not really using the new keyword.
Okay. So to take that a little bit farther, we never defined a variable named math, which would have been, we would have used the new keyword like we did out here. So we defined our instance of binary tree, we use the new keyword to call the binary tree constructor. So nowhere did we actually define a variable named math and set it equal to new something. Okay, so we don't have an instance variable named math, right? Okay, what else about the word? So that's really an important aspect of this thing. Compiles and runs. As far as we're concerned, nowhere in our scope is a variable named math, right? What's the other thing about math that lends us to believe it's likely a class? This is more of a naming convention thing. Yeah, classes very commonly start with capital letters. So now that's not a promise, but generally speaking, something that's built into the language, they follow that naming convention. And then as programmers, we also try to follow that naming convention. It's not illegal to name your classes with lowercase letters. Typically, classes start with an uppercase letter. Okay, so, reason we know this is a class or strongly suspect it's a class is we didn't define a variable named math. And as far as we know, we don't have an instance named math available to us. So this is likely a class name that's in a library that we have access to. And also, since it starts with a capital M, it's probably a class name. So since we have a class name preceding the name of the method, this method must be a class method. Now, if I were to go and look in the documentation and find ABS there, what would I see in front of the definition of ABS? I see the keyword static. So when we're defining a method, static says that a method is a class method. The absence of static means it's an instance method. So most of the methods we've written here, and well, actually all of our methods here in binary tree, have no static out front. Therefore, these are all instance methods, which means we call them using an instance of the class in which they were defined. Like we're doing out here, we're calling the add method using the instance of binary tree, not the binary tree class itself. That make sense? Okay, and here, let's just be complete here. So I'm going to jump into the Java documentation. Oh, I thought it might have been in the cache. It wasn't. All right, so I'm going to go to java.lang. Actually, I'll do it over here. So that's the default library that all Java applications come with. All right, and then down here, we're going to see a class called math. Inside the class math, we see a whole bunch of mathy stuff. First, we see a couple of constants here. We have e for exponent and then pi. So this gives us these, and these are owned by the class. So we'd say math.e or math.pi to get those two fields. Okay, then we have absolute value, all those things. So here's our absolute value of either a double or a float or an int or a long. So there's 4 versions of ABS. What is it called when we have the same method name with a different number and or type of parameters? Polymorphism. So here's an example of polymorphism here. So we're calling one of these guys. I think we're actually calling probably this one because our 2 guys were integers. So notice we have static in front. That tells us that if we were to call this method, we call it using the name of the class in which this method was defined, and the name of the class is math. That make sense? This shows us the other side of it. This is how we read the documentation and go and use it. Okay, so similarly, if we picked anything in here, let's just pick a random class here. We'll pick short. All right, so this is a class none of us have used before. All right, so let's look at so here's constructors for a short. So we pass it a short value, which is kind of a tiny integer, right? Shorts are 16-bit signed integers. So let's say I wanted to get the byte value of a short. This method right here. How would I call that method? Is it a class method or an instance method? And how do you know? Instance method, how do you know? No static in front. So since it's an instance method, we've identified it as an instance method because we don't see the word static in front of it at the method definition here. How do we call instance methods?
Use your instance.
Using an instance of the class in which the method was defined. And in this particular case, this class is called short. We would need to create an instance of short, and we happen to have a couple of tools here for creating instances. We can create an instance of a short from either a short value, or we can pass it a string that's a representation of a short. So we can pass it the string 13 or something like that. For bonus points, what is the largest short value? Or the smallest short value? It's the range of short values. Short values are 16-bit signed integers, right? Bytes are 8-bit signed integers. So that's negative 127 to positive 128. No, negative 128 to positive 127. So what's the range of values for shorts? You might have this on Jeopardy at some point. Well, it is kind of like in the same, from a computer science perspective, kind of in that same vein of like random questions you might have on Jeopardy, right? Like some obscure author of some book that nobody read, you know, something like that.
You should play that in senior sim, computer science Jeopardy.
So it's plus or minus 2 to the 15th power, because you need one of the bits for the sign. So that's negative 32,768 to positive 32,767. Okay, you need to have that memorized. You probably don't have to have that memorized. Maybe you should know kind of ballparky, right? Because isn't that the same? This is related to Unicode, right? Because a char is like a short, but it's unsigned. So a char is a 16-bit unsigned value. And that matches up to the Unicode character set, which is 65,536 unique values. So that's 0 to 65,535, which is the number of unique values. If you took the absolute value of negative 30,768, added to it positive 32,767, you get the 65,536. Well, 535, 0 to that. Okay, so everybody memorize those now? We got it? I lose my precision around, well, definitely at ints. So ints are plus or minus 2.1 billion. That's your ballpark. It's plus or minus 2 to the 31st power. So then add 1 or subtract 1 on the negative side, and keep it on the positive side. But then doubles are quintillions. I think quintillions. Yeah, it's like 9.6 quintillion, plus or minus that. It's a big number. So I got to work on that. So you work on memorizing the short. I'll work on making sure I get enough digits on that side. All right, so we would build a short using this. So I mean, this is a class we've never used before, right? Or most of us haven't used before. We haven't run into a need to use the short class before. But now, just by looking at the documentation, we know how to build one. We can call the constructor either with passing it a short value or passing it a string representation of a number. And now we see all these methods that work with this. Okay. All right, so we get our difference. If we're out of balance, then we're going to go ahead and print out how we are out of balance. This is going to actually be a decision-making point later on for actually putting things back into balance, right? And then we'll finally return true, because that's what this method said it's supposed to do. I'm supposed to scream true or false if I'm, whether I'm out of balance. But in the process, I'll spit something out to the screen. So I'm printing something as well as returning something, two separate things. Okay. Otherwise, if I didn't fall into the I'm out of balance trap, I'll just return false right here and say we're good. Okay, so let's go ahead and run this. And I think, yeah, here's my order, right? I'm going to add my stuff back to my tree. We should hard code our tree in here. Actually, we really should hard code our tree in here. That would make life a little bit easier. Okay, so then we'll go ahead and we're going to, actually, are we ever calling this? It's going to suck. That's going to suck. We did call we tested our get depth, right? That gets the depth of the entire tree. So let's then also go ahead and we'll print out is out of balance. All right. Whatever. I had it on this screen. Didn't I? Oh, there it is. 6, 5, 7, 7, 4, 3, 5, 5. And then we'll do get depth. Let's go look at our printout here. Depth was 4. We are out of balance to the left. Out of balance was true. Look at our picture here, and we are out of balance to the left. Okay, so was that was the homework? That fulfill? Everybody get that accomplished? Go ahead.
No, so supposed to specify whether it was out of balance to the left, right?
I did. Out of balance left. Yep, that's this if statement right here. So really, what I have highlighted there is was your homework. Throw that if statement in there, right? Okay, so next step. We know we're out of balance. We know how we're out of balance. Now what? Now we got to fix it. All right, so let's. I mentioned last time we have some different algorithms for self-balancing trees, the kind of popular ones. Or we have something called an Avl tree, and we also have something called a red-black tree. So before we get into the specifics of those algorithms, let's just stumble upon how we might fix this ourselves. Last time I kind of talked about, you pick a pivot point and you kind of turn it on that point, right? Now, an important aspect of being able to do that, both AVL and red-black trees, is it red-black or black-red? I think it's red-black trees. Fire before smoke, yeah, that's got to be it. For no good reason other than that's Connect 4 logic. So clearly they use that for algorithms. But I'm pretty sure it's red-black trees. Both of those algorithms rely on you testing and correcting a tree after each add. If you do 2 adds in a row, that potentially, you might get lucky and maybe one of the adds didn't knock the tree out of balance, so you wouldn't have acted anyways. But if you get the tree out of balance more than twice, it becomes very difficult to correct. You can pull it off, but you're substantially in better shape fixing it on each add because you know exactly where it got out of balance. Does that make sense? Okay, you can pinpoint it and then focus on that area. All right, so the last thing we added here, so let's see if we kind of just back up here. Let's take some of this extraneous stuff out because we know how we're getting our depth. That was from our recursive calls last time. Okay, so our tree looks like this. Let's remove this last 5. So we didn't do that guy. Are we out of balance yet? Nope, we have a 3 and a 2. So we're okay. All right, so we ask, are we out of balance? What's the depth of this guy? This is 0, this is 1, this is 2, this is 3, this is 0, this is 1, this is 2. 3 to 2, the difference is not greater than 1, we're okay. So this 5 right here that we added didn't break stuff. Now we add this 5, we do the Plinko thing. Okay, it goes to the left, it goes to the left, it goes to the right, it goes to the left. So now we have that 5 right down here. Then we ask the question, are we out of balance? Yes, we are. How are we out of balance? We're out of balance to the left. How do we fix it? How do I bring this tree back into balance?
You have to make the root nodes left node and root node.
Okay, so we're gonna grab the top of the tree there, right? And we're gonna twist it. Okay, so like this is a little doorknob. Okay, so we're gonna twist this guy. And I think what we looked at last time is I made our tree's head node or tree's root node point here, right? And then I detached this guy, and he sat there as a tree himself. All right, so let's do our step-by-step move. So the first thing I need to do is I need to temporarily hold on to this tree, right? So maybe I create a little variable called temp tree. And temp tree is going to point to the same place that the current binary tree's root points to, right? Top level. Then I can go ahead and I can make root point to the new top of the tree. Like this. Then I need to go ahead and disconnect this guy's left node. Pretty important because you might have basically like a Picasso-based binary tree if you forget to disconnect stuff. Because we might add this tree. So let's assume we didn't disconnect the left node of 6. And I go ahead and drop this guy in here. So 6 becomes the right node of 5. But he also has a left node back to 5. So you've created this loop inside of your tree that no longer makes your tree an accurate binary tree. Does that make sense? So it's pretty important that we disconnect this guy from his left child. All right, so let's start writing this in here. So are we going to call this, if we're out of balance left, we're going to call this a rotate right? Is that kind of a fair name for this guy? So we'll say public void rotate right. All right, so we're going to go ahead and we're going to create a, let's look at our binary tree real quick. All right, so we need this guy to be this is actually our left tree. Ooh, this is gonna be interesting. Yeah, that whole implementing this as a single binary tree backfired a little bit here, but let's see if we can hack this back together. We implemented it as a tree of trees, which means we don't have access to the root node. It's the top level. So this guy right here, when we notice we're out of balance, we're inside of this tree right here. So we have a variable instead of temp tree. Well, here we don't have a variable called root. Instead, we have a variable called this. Okay. That built-in variable, and that guy's a little bit protective against you changing him. so it's not going to let us say, well, we'll go ahead and let temp tree equal this. We can do that part. Okay, so let's start writing this so you kind of see the example. So we can say binary tree temp tree is equal to this. We're good with that. That works. All right. Then what we really want to do is we want the guy that points to the binary tree right here to point to that guy's left node. So the move we want to make is this. This is equal to this dot left tree. That's what we want to pull off. And that guy is, he's a special case in here anyways. It doesn't treat him as a real variable. If he was a variable, he'd be a final variable anyways, so he wouldn't be changeable. All right, so we do have a bit of an issue here with the way we've implemented our binary tree if we're going to do this as a self-balancing tree. The way we wrote it is great for just binary tree searching and adding. In fact, it makes life easier thinking about things as a tree of trees. But now that we want to rebalance this, we really kind of need a top-level dude to keep track of the top of the tree, right? All right, so this rotate right thing, as we have it written here, isn't necessarily going to work. So without rewriting our entire binary tree, how might we pull this off? Go ahead.
If you change the left tree to the left tree's left tree, the right to the left tree's right tree, and the payload to the left tree's payload.
Let me ask it a different way. What is anywhere in our program? Anywhere in our program. What is a synonym for this right now?
Main activity.
Yeah, so inside of our main activity, this dude right here, he's a synonym for this. So we could make that guy a class variable if we wanted to. We could also move him into the singleton. And we can change what that guy points to change the top of our tree. Does that make sense? So let's go ahead, and since we have our singleton, I'm going to get rid of him from here. Go ahead and put him up there, which then is going to break our main activity in a couple places. So we need to do core dots in here. So that's a core dot BT, core dot BT, core dot BT, core dot, core dot. All right, so we just move the location of our binary tree into our singleton. Make sense? All right, now when we go back into binary tree here, instead, so we're going to go ahead and we're going to remember this. If it makes us feel better, we could also say remember core.bt. We can give us another, those are synonyms, right? This is how an object refers to itself from within itself. Right now, we are within the binary tree class, so we can refer to ourselves as this. External to this class, we know that we have another variable that happens to point to the same place in memory, and that's core.bt. All right, so we'll set temp tree equal to core.bt. Then we're going to update core.bt to be equal to, we can say this is left tree. Let's just stay consistent for right now. We're going to say core.bt dot left tree. Even though they're synonyms, let's not mix and match. All right, so we're going to preserve our top level tree because that's really our root node, right? Our root tree is our global variable that points to the tree. That has a whole bunch of other subtrees hanging off of it, but that guy's the guy that's holding onto the tree. So I'm going to preserve him inside of temp tree. Then I'll go ahead and update that global variable to be equal to his own left tree. I would only be doing this if I am rotating to the right, which means that I'm out of balance to the left. Therefore, I know I have a left tree. I can't be out of balance to the left if I don't have any weight to the left. There's got to be stuff over there. Otherwise, it would probably be, we'd have to be careful and make sure that we don't set it to null values and stuff. But, we're calling this for a reason. All right, so now we have that. Next thing we need to do is we need to disconnect temp tree's left tree. Temp tree dot left tree is equal to null. Okay, so now we've unhooked it. Okay, so we've made, at this point, we've done this. We've made temp tree point to this guy. We've made core.bt now point here. Used to point here. Now it points here. And then we're going to go ahead and break this invisible line that was here, because this 6 used to have a left tree leading to this tree right here. We're going to get rid of that. So now that's null. So this guy is a free-floating tree, and this guy is a free-floating tree. We have a local variable that keeps track of what used to be our global tree, the top of it, and then we have a global variable that keeps track of kind of our new tree. Okay? Now, we're going to take our temp tree, and we need to add it to this tree here, as we're adding it as a child. Now, up to this point, our add, where's my add here? We only have one version of add, right? Yep. Our add takes in a payload, and based on that payload, it goes ahead and, depending on whether something is set, this guy right here is for the empty tree, right? For setting the payload the very first time. Otherwise, we decide where to put this guy, and we just keep passing the buck, passing the buck, passing the buck. Well, in this particular case, I don't have an integer payload I'm trying to add. I'm trying to add a binary tree. Does that make sense? So I want to do something pretty similar to this. In fact, logically, I want to do something very similar to this. With the difference being is that I'm not passing the buck for a payload, I'm passing the buck for a tree, for it to finally set his left tree. So we probably could engineer this where we could share the logic between the two, kind of, because it's really going to be identical logic, except one of them is placing an integer inside of a tree, the other one is placing a tree. But just to keep things simple, let's just go ahead and we'll just write the method a second time as if we're adding a tree, and not worry about sharing the logic. At that point, you're kind of trying to minimize your number of lines of code, and maybe then it gets a little bit confusing. The two methods then get coupled, all that stuff. But this would probably be one of those toss-up situations. So we'll say public Boolean add, but this guy's not going to take an int payload, because remember we're creating a polymorphism situation here. This is the same method name with a different number and or type of parameters. So this guy's going to take the same number of parameters, but it's no longer going to be an int. Now it's going to be a binary tree that we're adding. Okay? Now, we don't need to ask this if it's set question. Because then that kind of, I think maybe would break stuff. You probably could pull it off. You'd have to do something pretty similar to how we're doing the rotate right stuff with the global variable. But then at that point, we've made our binary tree coupled to that global variable. Well, we've already done that anyway, so that ship has sailed, I suppose. But in any case, we know we're not going to call this guy. We're not going to have an empty tree. We're going to say add this tree to it. Okay, we know we're not going to do that. If we were, we would just do the global thing. All right, so we're going to figure out where should this guy go relative to where I am right now. So we're going to say if bt dot payload is less than or equal to this dot payload, then it should go to my left. Correct? So now if I'm in here, I'm going to ask the question, do I currently have a left tree? If I do, then I'm going to go ahead and I'm going to tell my left tree to add this guy. So if this dot left tree not equal to null, this dot left tree dot add, we're going to call the binary tree version of add. Now we'll go ahead and pass him BT. Otherwise, if I did already have a left tree, I'm sorry, if I didn't already have a left tree. This is if I did. This says I already have a left tree. Okay, go ahead and this guy should go to the left, so go ahead and tell my left tree to add this binary tree. Now it's his problem. If I didn't already have a left tree, I'll say this dot left tree is equal to BT. I'll set it equal to that tree. Just hang it right there. Else, we should be adding it to the right. So we'll say if, and we could have done this as an else if, but we'll just keep it structured. This dot right tree not equal to null. So if we do have a right tree, then we'll say this dot right tree dot add BT. Tell our right tree to go ahead and add this guy. Else, we'll say this dot right tree is equal to BT. Make sense? So this guy's going to get called as part of our rotation function. And we will add that subtree, that temp tree. This guy right here. This hanging off temp tree is all of these other subtrees. So we're going to add this entire temp tree to 5, and it should then drop during this add thing. We're going to say, should a 6 come to the left? Is a 6 less than or equal to 4? Or is a 6 greater? Is 6 less than or equal to 5? Or is a 6 greater than 5? It's greater than. Does 5 have a right tree? It does not. So we're going to set this guy as 5's right tree. So that's our new tree after this is done. Paying very careful attention that we did disconnect 6's left tree from 5. And that's the big mistake that often gets made. You remember back when we were looking at linked lists, and I made a comment that when you're disconnecting something from a tree, like I always set it to null, even though it's not really important here. It'll be garbage collected, that kind of stuff. Getting into that habit of doing what you intend for it to do rather than trusting that it does stuff for you all the time will probably lead you down paths that run into less problems, like having a pointer somewhere 9 levels down in your tree that happens to point to the root node, which would be a difficult bug to track down. Because now you're getting lost in memory somewhere. All right, so you could make the argument that, well, why add an extra line of logic that happens by default anyways? More times than not, I find that being explicit usually keeps you out of trouble. So I would say do it, unless you're just really, 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 really confident in something. But even then, probably still do it. Okay, so this should be our new tree when all is said and done here, correct? Is this guy out of balance? If we were to ask, are you out of balance? He's going to come back with, no, this is 0, this is 1, this is 2, this is 3. This is 0, this is 1, this is 2, this is 3. We're perfectly balanced, actually. Okay? We're not even within 1. We're, boom. We're spot on. Okay. So let's go ahead and test this guy because we know that our tree is out of balance left right now, right? And we've only written the rotate right. Okay. And then I'm going to change our tree here in a second to show how AVL works. Okay, so since we are out of balance, I still have a bug in here?
It wants a return type.
Oh, because that guy returns true.
Yeah.
Yeah, so we're just going to say that it just always works. We're happy. Okay, so now what we'll do is this is where we're printing whether it's out of balance. So we'll do it out here so we see the individual steps. So we're going to have a Boolean out of balance is equal to this guy. So the result of calling is out of balance. Then we're going to print out of balance. Then we'll ask if out of balance. And for right now, we know it's out of balance to the left, right? So we'll go ahead and we'll call the correct thing. So we'll go ahead and say core.bt.rotate right. And then we'll go ahead and print out of balance again after we rotate right. So the second time, it should be in balance now after we've rotated. So we'll check it. We know something's wrong. I'm not actually figuring out which way we're out of balance at this point. We'll have to add that in here in a second. But, you know, we happen to know the nature of this tree. We're out of balance to the left. So we'll go ahead and rotate right. We'll ask again, are we still out of balance? And we'll print out, hopefully, false. We're not out of balance anymore. All right, so we'll get depth. Then we'll go to our monitor. We're out of balance left. Out of balance or true. Oh, then we're still out of balance.
Did you actually put the add in the rotate right?
I believe so. Well, let's make sure we actually called rotate right. Yeah, here's our rotate right. Go into binary tree. Oh, I get what you're saying. Did we finish writing rotate right? Possibly not. But we didn't. So then we'll go ahead and we're actually this stuff. So we should say core.bt.add temp tree. It's that last piece. Oh, good. Hopefully it works this time. Otherwise, I'm just going to be disheartened. It's going to be my first bug ever. 6, 5, 7, 7, 4, 3, 5, 5. Get depth. Okay, good. So here's our out of balance left. We are out of balance. Then we called our rotate, and we're no longer out of balance. All right. All right, so let's look at something else here then. We go ahead and put this tree back to the way it originally was. Let's see, this will be That's how that tree would look with the 3, right? Okay, we're still out of balance, right? We're out of balance at the same depth as we were before. So if I do my rotation, I'll make sure this is going to be the right example. So I do this. Well, actually, this is going to work this time. So when I drop that here, yeah, we're in balance. See, with AVL trees, oh, it's because we're not doing it from the top level. All right, so we would call this, what we just did here, a pretty generic rotation, where we're dropping an entire tree in and things like that. What the Avl rebalancing algorithm does is it looks at subtrees. So rather than rotating the entire tree here, it's going to go down and say, okay, well, this is the last dude you added. So rather than fix this entire tree, which might take, I guess a lot of work moving things around in memory and stuff like that, we're going to go ahead and we're going to fix this part of the tree. Maybe just rotate this guy. So what if we picked this as our pivot point? So all of a sudden the 4 drops down here. The 5 goes to its right. So let's we'll just move these so we can visually show it. So that becomes that, correct? We're still out of balance. So when we're out of balance, so that original out of balance in an AVL tree is called, it's not just out of balance left or out of balance right. It's left left or left right or right right or right left. Which side we're out of balance? Let me actually show you the diagram for AVL trees. We have some decent diagrams down here for the rebalancing. I thought they had better pictures than that. Yeah, these are actually new pictures. It's possible they are better pictures. Let's find out. So far, I don't think they're better pictures. Okay. Because when we're left out of balance, we do a single rotation to the right. When we're left right out of balance, we rotate left and then right. It's 2 steps, so you kind of climb the side of the tree to get yourself back into balance. Yeah, so what we've done here is a simple rotation. So figure 4 shows a right situation. Is that this guy up here, or is that below? Okay, this is figure 4. So this is out of balance to the right, then the right. So it's going to pull the T4 up, and this guy actually switched to the other side. So we picked, so this would have been a This was a rotate left because we're out of balance to the right, where we were out of balance to the left and we did a rotate to the right. So root of the subtree to be rotated left. We pick that top level. Now notice they have a little stem coming off this guy. So rather than them doing the entire tree like we did, they zeroed in on the portion of the subtree, the subtree within the tree that they wanted to rotate, to try to bring that back into balance. So if we're just out of balance to the right, then we can try to fix that subtree, effectively changing the order in which we would have added stuff to the tree. So let's see, do they do a left? I guess we could just make it backwards. So X is the root of the subtree. So for us, this would be core.bt. That's what we had this thing set as. Z is the right child that is not left heavy. So this is right, out of balance. Okay, so this tree is right heavy, and the entire tree is out of balance to the right, and that this subtree is right heavy. All right, so this is right out of balance. All right, so when we rotate this, the X dropped down, the Z pulled up, and notice that the X's right subtree now is the old left subtree of Z. So when we turned, the X dropped down, this guy became the new root. We disconnected this guy's left child and re-added it to this guy, which made it drop down here to the right. So we did a very similar move to what we did before, except we disconnected this guy's left child, the guy we were bringing up. So we preserved the left child of Z. This is going to be our new root node in an AVL rotation. So we took this guy off, we disconnected Z's left child. We had a pointer pointing to this guy. Then we rotated Z up. So we rotated, this is a left rotation because we're out of balance to the right. So left rotation. So Z becomes the new root. X becomes the left node of Z using the same algorithm we used, where we disconnected X, we dropped it in on top of the Z and let it add itself to the tree. Okay, so we know that Z is greater than X by our binary tree rules. When we added Z here, it was and also by alphabet. All right, so when X became the new root, and then when Z became the new root and we added X to it, it would have plinkoed to the left. Okay, so that's where this X lands here. So we didn't just rotate it and just drop the X down and just pretend like everything works. We're safer to preserve this tree. So this is our new root, and we're going to preserve this guy in a second, and you'll see why. So we preserve this guy. He rotates up. We preserve this guy because he's going to be our temp tree. We're going to add... Seems like that maybe is worse. Okay. We're then going to disconnect our old root's right node from Z. So we've preserved both those guys. So this little line here is going to scribble away. So it's no longer attached. Then we're going to try to add X to Z. And the problem with this is if I add X to Z right away, Z already has a left child. Right? So when I add X here, it's going to try to add it. It's not going to be able to just immediately put it as a left child. It's going to say, oh, well, this guy already has a left child. Therefore, let's go ahead and ask him, pass the buck, ask him to add this node as the left child. And at this point, we're not necessarily sure which is, well, we know this guy is greater than X. Otherwise, it wouldn't be on the right-hand side of X to begin with, right? So we can, their naming conventions are a little bit funky here. But so X is disconnected from Z. Z becomes the new root. So as of right now, if we just kind of pretend like this left side of the chart is gone for a second, our tree looks just like Z. So it's Z with 2 nodes hanging off of it. Now if we just try to add X to that, X is going to drop into the Z, it's going to flow to the left, and then it's going to flow to the left of the next guy. So now all we've done is we've made it out of balance to the left. Does that make sense? It's like, great, now it's just out of balance different by doing what we just did. When we preserve the X, disconnect the X from this, set the new root node as Z, preserve Z's old left node, disconnect it. So now Z is free and clear on the left. Then we can go ahead and we can add X to Z, which will have X drop directly to its left node. Then add this preserved node to Z, which will drop down to X, which will then go to the right of X, which now will be back in balance. See how the T23 is no longer the left child of Z, instead X is the left child of Z and T23 is the right child of X. We added X to Z first, then we added T23 to Z, which flowed to X, which flowed to the right, because we know this guy must be larger than X because of where it was placed in this original tree. Kind of following how Avl trees are a little complex? Okay, not the friendliest thing in the world. Now, what I think is going to be helpful is if we find an example where we're weak here. It seems like our rotation across the top level here will work for this tree, right? Yeah, I think so. So we rotate that to the right, we drop it in to the right hand side, we're in balance. What if we go to the left side? Maybe the left side is where it'll break for us. So we'll need a couple of, so we're going to need a path of least resistance will be another 7. We're still in balance. Then another 7. We're still in balance. And then another 7. Now we're out of balance, right? We have 2 layers. So this is 0, 1, 2, 3, 4, 5. This is 0, 1, 2, 3. So now we're out of balance. Our approach here would be to now, before we rotated right, now we would do a simple rotation left. So kind of the same thing we did before. So let's see if we can get it to break. So what we're going to do is we're going to go ahead and we're going to preserve our temp tree. So this guy here is going to be our new core BT, right? So we'll preserve our temp tree here. Point that up here. Core BT will go right here. So that becomes the new top level tree. So now what I'm going to do is, here I need to pretend like that's still attached for a moment. All right, so here we'll hide that down there for a second. There's our temp tree. There's our core BT. So now when we go to try to drop this temp tree on top here, what happens? Is a 7 less than or equal to, is a 6 less than or equal to 7, or is it greater than 7? It's less than or equal to, less than or equal to, less than or equal to, less than or equal to. We just made a bad situation way worse by doing a simple rotation. So this wasn't a catch-all. It worked well when we had a problem out of balance to the left. But when we forced it out of balance to the right, it failed to work. And I don't think that's even a global truth. I think there are situations where we can be out of balance to the left, and it would still break, depending on what the right looked like. So the issue is that treating the entire tree as a gear isn't as foolproof or as simple as it initially looked like it would be. Does that make some sense? So that's where let's see, it would look like that. So this is our current out of balance tree, correct? We would say that this guy is out of balance, definitely to the right, but then to the left. It's a left heavy out of balance. And the move for this would be a rotate right and then a rotate left up the tree. So it's two different rotations because this is like the more cryptic out of balance. So we're out of balance to the right, and then we're also out of balance to the left within the right. So what we need to do is we need to rotate. We pick a pivot point. And I think this is the pivot point. So we'll pick a pivot point, and we will rotate here first. Okay, so let's see what that rotation ends up looking like. We know that the problem is here because we're out of balance to the right. We're also then out of balance to the left. And that second way we're out of balance gives us the information of whether we're doing our simple rotation or our complex. Is it a simple right rotation, or is it a right then a left rotation to kind of climb up that side of the tree? Does that make sense? So in this case, we're kind of out of balance in, let's call it, the worst way. All right, and we just saw how bad it would be if we just used our standard approach. So we're going to pick this guy as our pivot. So what we're going to do is we're going to rotate to the right about him. So he's going to drop down here. And this becomes our new subtree. Now the problem here is that that's not a legal tree. Right? For the time being, that's an illegal tree. So we certainly can't leave it like that. Now, the good news for us, for at least a moment, is we're not done rotating. The bad news for us is even when we do our rotate to the right, this is still putting us in a position of being illegal. Let's go back here. I know I need to rotate to the right first. So when we're out of balance, we need to rotate. Yeah, we need to rotate the right, then we need to rotate to the left when we're out of the balance right, left. All right. Let's see if they give us a simple picture for this, because I have too many nodes here to really show this good. But there, we only have a few minutes left, so I'll walk it at least a little bit. So I need to do two different chiropractic adjustments to this tree in order to get it back into balance. What would happen if I rotated the entire tree using our simple rotation to the left? We saw that what would happen a few minutes ago, right? It does the crazy things hanging all off the left-hand side. What if I rotated to the right? I mentioned that we do a right rotation first. If I rotated to the right, what would happen? So let's do our simple rotation that we had before. We'll point to this guy. That's our left tree, or that's our temp tree. This guy is going to be, let's see, rotating to the right. We're going to go like this. No, I'm doing the opposite. I want to rotate to the left. So that's going to be my temp tree. This is going to be the new top. Ooh, what did I do? I can then grab this whole subtree and that's the way we did it before. That has the thing hanging off the bottom. Now I'll go the other route. So we want, if we're rotating to the left, this guy is going to be, no, I need to rotate it to the right. See, I told you this is confusing. I told you it's confusing. So when I rotate this to the right about that, the 5 becomes the new root node. So this becomes the new root node. I'm going to preserve the old top of the tree. So now I have this entire tree kind of hanging off here. This is the new top. I'm going to then take this tree and I'll add it onto that guy there. As our first move. Well, as a first move. Is this still a legal tree? All right, we're in better shape than we were a second ago. We're a legal tree. Are we still out of balance, though? Yeah, we're still out of balance. All right, so are we even less out of balance? This is 0, 1, 2. This is 0, 1, 2, 3, 4, 5, 6. We're more out of balance now than we were before. So now we need to do another rotation. But by having that top level rotation where we started at the very top of the tree rather than singling in where the actual problem is, we lose all sorts of precision on how bad we're going to knock it out of balance. Does this feel like it's the correct first move? This does not feel like the correct first move because we start at the top of the tree. Just because we're out of balance to one side, would you say that this is a pretty unpredictable type tree? I mean, that's a lot of 7s in a row, right? But it's a legal tree. So the point here is that knowing how your tree is out of balance doesn't necessarily give you all that much information about the structural integrity of your tree. You know, what it actually looks like. You might have a very full-featured tree on both sides. It just has a little bit of unbalance on one side. In this case, we don't. In this case, we have kind of a worst-case scenario, which is why we usually show this first, even though it's still hard to explain, where when we disconnect this entire tree, if we start up here, one of these top branches, I mean, you're basically trying to, I mean, it's you know, you have a depth of 5 that you're trying to add anywhere else in your tree. So what we really, if you were just to look at this as a human being and say, what would the path of least resistance be to get this tree kind of an equal depth? You would say to mess with stuff on this side, right? But isn't that going to involve us getting stuff from this side and recruiting it over to this side? Similar to what we saw in this example here, where we disconnected a tree or disconnected a leaf node and then re-added it. It's going to have to be something like that because we saw we can't create a legal tree on this side, right? Just by doing a simple rotation. So we know we're going to have to reshape this guy, this side. That's where our focus needs to be. But we can't create a legal tree out of that. We're going to have to start bringing stuff from this side over and adding it as subtrees over here. We can certainly see that if I took this 6 and I added it as a subtree over here to one of these, that might start working. Does that make sense? All right. So let me do this. I'm going to give you this as your homework assignment. I'm not going to give you coding to do. Okay? I want you to read. Read is maybe a tough thing. Attempt to understand the Avl tree rotations for Tuesday. Okay? I will likely give a quiz on it, where I'll have the 4 different out of balances. Left, 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 right, 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 left. And have you tell me how to rotate those. Once you understand the concept of it, it's not that bad, and actually writing it isn't horrible, but you have to draw a lot of pictures. Okay? So reading assignment, I'll put this up on Slack, and I'll see everybody on Tuesday.